Good evening, and welcome to the Scientific Adventures of Beardman. Today we're going to take one more look at Newton's second law. Because at the moment we have F equals ma. Okay, a force causes a mass to accelerate at a certain rate. Okay, we think of the force as the cause, the acceleration is the effect or the description of the motion, the change in motion. But there's an equally good way of looking at this law, and that is if we break down the acceleration. Because in a way, the real change we're looking at is a change in velocity. So of course, acceleration is the rate of change of the velocity. In other words, the change in velocity divided by the change in time. And so if we take a look at that, we could see the change in velocity as a description of how the motion was changing, but the time is really the amount of time that force is pushing for, right? It's the amount of time that the object is accelerating. And so that really has more to do with the cause than the effect. And so if we take that change in time and move it on over to the other side, then we have the two things that are causing the change in motion, the force times the change in time, and we have that equal to the mass times the change in velocity. So now on the one side of the equation, we have the two things that are causing the motion, the change in motion, the force and the change in time. When we multiply those together, we have a special thing we call it. We call it the impulse. The impulse on something is the force times the amount of time that force is acting for. Okay, the amount of time that force is pushing on the object. On the other side, we have the mass of the object, and we have its change in velocity. Okay, well, mass times velocity, we have a special name for that. We call that momentum. There's even a symbol for that, which is a lowercase p. And so since the mass of the object won't be changing, my mass won't change, except for at Thanksgiving dinner. That was mighty good. But you get the idea. As the object is being pushed, we aren't changing the mass of that object as it's being pushed along. And so that object, the thing that will be changing is its velocity. Okay, so mass times the change in velocity, we could also write as the change in momentum, which is describing how the object changes its velocity. So, why is this helpful? Well, this is often helpful in, probably the easiest way to say it is collisions, when one thing runs into another thing, whether it's intentional or unintentional. And we can see that if we want the change in momentum to get bigger, in other words, we want the object to get going faster, or we want it to drop to zero, either way. If we want a big change in velocity, like when we're kicking a soccer ball, well, when we're kicking a soccer ball, we can get a bigger change in velocity by either increasing the amount of force or by increasing the time of contact. Well, now the force, we see soccer players trying to increase their force by working out in the weight room. They get bigger muscles, they can put more force on the ball. Okay? But the time of contact has to do with something else your coach has told you. And not just soccer coaches, but any coach will tend to tell, any coach involving getting a ball moving will tend to say this, and that is follow through. When you follow through, when your foot swings through the ball and the ball stays in contact with that foot for a longer time, it has more time to accelerate or more time to change its velocity. And so you get a bigger momentum or bigger velocity in the object in the end. So there are two ways to increase the velocity of an object. One is to increase the force, kick it harder, or hit it harder, or to increase the time of contact by following through. Okay? Now, other situation that we often have is a situation where there are changes in a constant change in momentum that we're looking for. For example, anything we want to bring to a stop. Okay? If we have some object like it's falling and it's going to hit the ground, well, that object has a certain momentum. It's going to end up with a momentum of 0 because it's falling and it hits the ground. Okay? So in that collision with the ground, well, what's going to cause it to stop? Well, it's a force acting for a certain amount of time. Okay? So there's two ways we can bring that object to a stop. Well, in general, okay? We can either have a really big force for a very short time, or we could have a very small force for a very long time. Okay? If a big object, if a car is rolling towards you, if you're really strong and you just stop it, you could put a big force for a very short time. Or if you were a little bit smaller, like a 4-year-old or something, then as that car is rolling towards you, you could put a little bit of force and just keep backing up with it and keep backing up, but a little bit of force over a long time. And eventually you'll bring that car to a stop. So how does this apply? Well, as something hits the floor, like let's say we drop a champagne glass, okay? As that champagne glass is falling, it gains a certain amount of momentum. And when it hits the ground, we used to talk about when it hits the ground, it's like being the end of our sequence as we were in free fall. Now we're talking about the collision. And so when it hits the ground, that begins our event, okay? And as it hits the ground, it's going to come to a stop. The question is, does it come to a stop with a small force over a long time, or a large force over a short time? Well, we can see that happen when that champagne glass hits tile or cement. That would be an example of it coming to a stop in a very short time. When it hits that, there's no give, okay? And so it has to come to a stop almost immediately, which means a very big force, which means it shatters, breaks. But if you drop it on carpet or on a bed or something like that, well then there's some cushion. And so it comes to a stop over a longer time. And so that increased time of impact allows for a reduced force, and the glass doesn't break. It just kind of bounces. Okay? And so we see this in many situations. Of course, there's some where we want the object to break. For example, I go out and I'm chopping wood. I give my axe as much momentum as I can, and once that momentum has been given to the axe, it's going to come to a stop. But the question is, does it come to a stop in a small time, causing a lot of force that'll split our wood, or does it come to a stop in a long time, which reduces the force and may not split the wood? Well, how do we do that? If we're splitting wood, we put it on cement or on a stump or something with as little give as possible. Okay? We would never put our log that we're trying to split on a bed. We would hit it with the axe, and the axe would come to a stop, but because of the give of the bed, it would come to stop over a long period of time, which means a very small force on the log, and the log wouldn't split. It just wouldn't happen. So you can see this idea of the impulse causing a change in momentum, especially looking at the impulse here. We can see that force times time, we can increase the force or increase the time, and either one will give us a situation where the object will come to a stop. Depends whether we want to have the object have a lot of force on it or a little bit of force on it. All right, well, thanks for tuning in at our last look at Newton's second law as we rearranged it to get the equation that lots of people say is impulse equals the change in momentum. All right, we'll see you next time on the Scientific Adventures of Beardman.